So hello everyone, today we are going to look into shift operators in Java. So basically we have two types of shift operators, the left shift and the right shift. And basically what the operators do is simply move a bit towards the left or towards the right. So basically we can specify the number of bits to move towards the right side of the operator. I'll show you an example. So basically we have an example here where we are using the left shift operator on the number 10 and we want to shift the number of bits two times. So basically what that means is simply shift the bit towards the left two times, right? So I will be showing you and explaining you in detail as well. So here you can see that we have two types and we'll be exploring this as well. Unsigned right shift, so the symbol for that is three right arrows, right? So let's look firstly at the left shift operator, right? So I'll show you example first in the drawing itself, and later we'll be seeing a running example in the IntelliJ, or what the name is. Yeah, it is IntelliJ, I guess. So anyway, moving to the left shift operator. So let's say we take a number 9 and we use the left shift operator on it. So let's say one times, okay? So basically this will specify the number, right? And this will specify the times to shift, right? So let's see, we have 9 and in binary we represent 9 as 1001. So basically this is 2 to the power 0, this is 2 to the power 1, this is 2 to the power 2, and this is 2 to the power 3. So simply add plus 1, which is 9, right? So this is our layman binary representation. But we know in Java integer is of 32 bits, right? And out of that, 1 bit is always reserved for sign, right? So leaving that 1 bit aside, we have 31 bits that we can work with. So let's see how we represent 9 in an integer that is 32 bit, right? So that the negative sign. So as I specified, this 1 bit will be used for sign, and basically here 0 means positive and 1 means negative, so I'll mention that as well, right? So for 9 it is a positive number, so we'll be having 0 at the start, right? Following we will have, let's say, 7 more zeros, followed by 8 more zeros, followed by 8 more zeros. This makes up for the 24 bits, okay? Then we'll be having 0 0 0 0, followed by 1 0 0 1, right? So this will be our binary representation of 9, okay? And I have used this method to define these 24 bits so that it is easy for us, right? So these are all zeros, so I have used this, otherwise we will have to write 0 all over the place. Now let's move the bits towards the left. So we were doing this, right? So let's move the bit toward the left. So these first bits will remain the same because we'll be moving these towards the left, right? So basically this is what will be happening, and the last bit it will be replaced with 0. Let me show you. So we have this here, okay? So we have those 24 zeros. I will just write that. So 24 zeros followed by now 3 zeros. So we shift the 1 towards here, so we have 3 zeros followed by 1 0 0 1, and at the end we will again replace it with a 0, right? So now let's see what's the binary number for this. So this is 0, let's ignore it. This will be 2, this is a 0, ignore it. 0 we will ignore, and this will be 16, which results in 18, right? Now this 18 is a decimal number, and this whole thing is a binary representation of 18. So I'll remove that. Okay, so we can say that when we use the shift operator on 9 once, we will get the number 18, right? So let's put it to test as well. So I will delete this statement and this one as well. So let's run this. So you can see I have defined x as 9 and we are using it one time and two time. So on running it one time, we can see that we get the expected output here, right? So we were expecting it to be 18 and it is 18. Now let's see when we do it the second time, right? So this means we do it one time, this means we do it two times. So we have already done it one time here. So now let's do it one more time. That would make it move towards the left two times, right? So now we have the same 24 bits which are 0, right? Then we have the three zeros. Now we'll be having two zeros because obviously they will also move. So basically two zeros, 1, and followed by 1001, and then we will be having 0, and now one more 0 will be inserted because we are moving towards the left, right? So every time we move towards the left, vacant space is created and that should be replaced with 0, right? Here it is this one, above it was this one. So now replacing the values, ignoring the zeros, this will be 8, ignoring this will be 32. Right, so basically it is in two powers, right? 2 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, and 32 plus 8 simply adds up to uh, wait, this will be 4, right? So this will be 36, and that is what we expect, right? So basically we were getting 36. So yeah, so that is basically the left operator, the left shift operator. Now we'll be looking into the right shift operator. Okay, so I hope you have a clear idea about the left shift operator. Now let's move to right shift operator, right? So I'll create a new page and let's go with the right shift operator, right? So let's look into the same number 9 and let's try to move the shift bits towards the right now, right? So let's create the solution for this statement. So the similar 24 bits at the starting, okay, followed by 4 zeros and then 1001. So we have the typical 9 where we started at the left shift as well. Okay, so we are again back at this stage. So what we want to do is move the bits towards the right this time, right? So this will be going right, this will also be going right, this will also be going right, and this will go in right, so it will be lost basically, right? So this will take place right here, and this will also be followed, but we are ignoring the zeros because they don't really hold any value, right? So that would result in 0 24 times, followed by 4 zeros, followed by one more 0, and then 100. So these are 4 and these are 4, right? Makes easy to read, right? So we ignoring this, and this will be, so 2 1 2 to the power 2, so that should make it 4, right? And let's check it as well. So I'll uncomment this for you. This is the right shift operator once and this is the right shift operator twice. So let me run this as well. And yes, it does return 4 and we did expect 4. So yeah, that looks quite good. And now we'll be checking it for the second time, and as we are seeing here, we should get a 2. So let's put that to test as well, right? So we have done it once, now let's do it twice. Now this will be the answer for 9 towards the right, but 2 times. Okay, so similar to the above, we will copy it, 24 times 0, followed by 1 2 3 4 zeros, then again, so this will be shifting, right, as we just discussed. So this will be shifting, 4 zeros remain 4, then again we get a 0 here, followed by 1 and then 0. right? So this last bit is obviously moving out of a reference every time, right? And a 0 is being inserted from the left hand side. Okay, so basically now what we have is this is a 0, ignore it, and this will be 2 because 2 to the power 0 and then 2 to the power 1. So we should be having 2 and we were expecting 2, so yeah, that is definitely right. Now you must have noticed a thing here that in the left shift operator, like we first had the 9 here. Okay, first we had 9. When we moved it one time, we got the 18, right? And then we got the 36. Now do you catch a pattern somewhere here? Then 36, right? So basically what we are doing is simply we can say that we are multiplying by 2, right? And that is basically what we are doing because binary numbers are basically base 2. So basically we are moving towards the right, which means increasing the power by 1. So basically in binary, we know that we have 2 to the power 0, then we have 2 to the power 1, then 2 to the power 2. So when we move the digits towards the right, we simply are saying that we are multiplying it by 2, right? Because 2 to the power 0 is 1, 2 to the power 1 is 1 into 2, and 2 to the power 2 is 1 into 2 into 2. So that basically means that we are multiplying it with 2, and that is definitely what we do get. However, in the right side operator, also we should see a pattern here, right? So firstly we had 9, okay, then we got to 4, and then we got to 2. So we can see that we are basically dividing the number by 2, right? And that works just fine. So basically that is also quite expected because we are moving towards the right. So basically 2 to the power, we are decreasing a power for by 2, again we are decreasing a power by 2, so on and so forth. So that is basically dividing by 2. So these operators are used in basically DS equations everywhere, like dividing by 2 or raising to the power. That is basically something that these operators are basically capable of. But basically we can also have other implementations as well, right? And now I'll be showing you for the final operator, that is the unsigned right shift, right? So let me show you. So basically we just saw the right shift, okay? So we saw the right shift. So basically the right shift is two arrows towards the right, right? So this is also called signed shift, right? Okay, so basically the sign is maintained here. But in the unsigned, so basically for unsigned we have three right arrows. Okay, so we have an unsigned as well, unsigned right shift. So it basically shifts the digit the uh, so the unsigned right shift basically moves the signed digit as well. Okay, so this basically works on the negative only, negative bits only, but for positives it would work exactly same as the right shift as we discussed above. But this one basically, let's say, I'll explain with an example so that would be easier to understand. Let's take the 9 we had and convert it to negative 9. Okay, so now we will be using negative 9 because unsigned basically works the same if we use the positive number, but with negative number it works differently. So to represent 9, as I discussed above, that for negative number we set the bit the for a negative number we set the leading bit, that is the parity bit, or you might say the sign bit, we set it to 1. So basically we'll be having a 1 at the start. Okay, then we have zeros. Okay, and that would be approximately, wait, let's say 7 zeros with this one. Okay, and 8 zeros again, 8 zeros again, and then we would be having 9. So 0 0 0 0 and 1 0 0 1. So this would be 9, right? Because these result to 9, and this represents that it is a negative, so this is a negative 9. Okay, so basically what the unsigned right shift operator does is that it moves it towards the right, even the sign bit. Okay, so these all will also move towards the right, and this will turn into a positive number. As I told, that a 0 will be inserted any time. Okay, even in any case, if we are out, we are removing from here, so we are inserting a 0 from here. In the left shift operator, we were inserting a 0 from the end. Okay, so in case we are left with a vacant space, we enter a 0, right? So in this case also we'll be entering a 0, not a 1, obviously, because 0 is the default value, right? So we insert a 0 and that would become a positive number now. Okay, so let's say that we'll be having a 0, then a 1, then 6 zeros, then 8 zeros, then again 8 zeros, then 0 0 0 0, then these have also moved to the right. Okay, so again we'll be having a 0, then 1 0 0, right? And that should result in a, let's say, this will be 1 2 4, so that should get us a 4 positive. But wait, I'll show you. We'll run it in real time and see what is the output. So let's say x is minus 9, and let's move it towards the right ones. Okay, with the unsigned shift operator. So we'll run it, and you can see that is pretty much not what we expected, right? So basically we were expecting 4, but we got a huge number here. So that has something to do with how Java stores negative numbers. So let's say we stored negative 9, right? So negative 9 is not stored like this in Java, right? As we discussed above, this is not the format that Java likes to store. It basically, let's firstly take it to our is, so we had this 0 7 0 8 0 8 0 0 0 0, and then 0 1 0 0 1, right? We had this. But Java basically, what Java does is basically takes 2's complement of it and then stores it. So running 2's complement on it first. So if you don't know what a 2's complement is, so basically we take 1's complement first. So 1's complement is simply inverting the bits, okay, and then simply add 1, right? So I'll firstly convert it to 1's complement and then add 1 to it. Okay, so first complement is basically inverting all the bits. Now the inverting is done not with the sign bit. Okay, so 1 will remain 1 only. Okay, other bits will be changed. So this will be 1 of 7 times 1, 8 times 1, 8 times 1 again, then 1 1 1 1 0 1 1 0, right? So this is the first 1's complement. Now we have to add 1 to it. So basically if we add 1, that would basically result in 1 1 7 times 1 8 times 1 8 times 1 1 1 1 0 1 1 1. So that is our number. That is how 9 is stored in Java. This is 9, negative 9. Okay, so now we'll be running the right shift operator on this. So let's say the right shift operator here, and also not to mention we'll be using the unsigned one, because that is what we are exploring right now. Okay, so let's move them towards the right. Now we'll be having a 0 followed by 7 ones. Okay, followed by 8 ones, 8 ones again, 1 1 1 1 1 0 1 1. That's 4, that's 4, right? So that is the number that we should be getting, right? So let's not account for this one. So this is 4, we know, right? And this is our sign bit, so it is a positive number, we know for sure. But what is the number, right? It is quite a big number, because 2 to the power 1 0, 1 and so on so forth till to the power 31. So we can say that the number is positive 2 to the power 31 minus 4, right? Also, we should be noticing that the integer strength or the integer range is between 2 to the power 31, right? So you can see that we have a negative number more, but we have only, you can see the end digits here 47 and 48. So basically in Java or in any language for instance, we have the integer from 2 to the power 31 in the negative side till 2 to the power 31 minus 1 in the positive side. So this is specific about the integer here, right? So we expect the number to be 2 to the power 31 minus 4 here. So here we discussed, let me remove this bottom thing that I just discussed. So we expect it to be that, right? So let me do it real quick for you. So you can see 2 to the power 31 minus 4 is 214748364, and which is pretty much what we get here, but it is a one less just because to the issue that I explained right now, that in the positive side we have one digit less, right? So that is the issue why it is that. Otherwise, if we were to take the limitations beforehand only and remove the one that we mentioned, right? So it should have been positive of 2 to the power 31 minus 1, because we obviously should know that the positive range is limited, right? So overall it is a positive, then we subtract 4 from it, then we should get the expected output, right? The thing that we are getting here, right? This whole integer, we should be getting that. Finally, I would like to highlight this special point that Java likes to store negative values in 2's complement. So you might find yourself in issue while working with these operators just because you are using a negative value. So make sure that you remember this fact and stick to it. Other than that, I would like to recap something real quick. That left shift operator simply moves the bits towards the left. So if we take this 4-bit number 1001 and we move it towards the left, a 0 is inserted towards the end and we get 0010, which equals 2. Now this does not act as you expected, because we just said earlier that it should be multiplied by 2. But that is not the case here, because we are not using a 32-bit string, 32-bit number here, we're using just a 4-bit number. So that behaves differently in that manner, right? For the right shift operator, we have two types, signed and unsigned. For the signed, we use two right arrow brackets, and for the unsigned, we used three right arrow brackets, right? And the unsigned one was specifically used for with negative numbers. Let's look at the signed one first. The signed one we will take, let's say 1001, which is 9. We move all the bits towards the right. The 1 here moves out of scope. The 0 also is inserted towards the starting. So this 0 is inserted new, and this equals 4, right? Now we'll be looking at unsigned one. So for unsigned, we are taking a 5-bit number, because we need to mention a sign bit as well, okay? Because sign bit is involved in the unsigned one. We specifically use it in the negative one only. If we use it in positive, it behaves same as the signed one. So for this we have used a 5th bit, which is 0 right now, which is 1 at bit, which is 1. So now I will be telling you about the unsigned one again. So for unsigned, we'll be having this 1, which is a sign bit. So basically, unsigned one is specifically used with negative numbers. Otherwise, with positive numbers, it would behave like signed only. So here we have mentioned 1. This all moves towards the right, and a 0 is inserted towards the starting. Okay. So now this number will completely change into a positive number. So everything will move towards the right, and we will get this number. So basically 16 plus 8, which will basically result in 24. So we can say that Negative 9 with an unsigned right shift operator 1 times results in 24. So that is it about this video. I hope that this video helped you in understanding and visualizing this.